Morning, everybody. So on Monday, we started talking about this idea of free radical chemistry. What is a free radical? It is an atom with an unpaired electron. That is correct. Are they reactive or unreactive? They're actually quite reactive, right? So electrons like to be paired. We like to have octets, the whole 9 yards. And so we also learned that radical stability kind of follows what other kind of stability? Carbocation stability, right? Except free radicals rarely rearrange, right? Radicals can be delocalized by resonance, but they don't rearrange like a carbocation rearranges. And so we started talking a little bit about why free radical chemistry was important for you all to know, in large part because it is the predominant chemistry in biology, medicine, those types of things, and we talked about some of those examples. And then we started talking about the free radical mechanisms in general, right? So we're going to be pushing single barbed arrows to show the movement of single electrons. So there's actually going to be some more arrows involved than were involved in the previous mechanisms that you all learned about. Okay? There are 3 steps to all free radical reactions. They are what? There's initiation, propagation, and termination. Okay, so all of your free radical mechanisms will have those 3 things in common. Okay? Now it turns out for those of you who are in polymer science, knowing initiation, propagation, and termination is going to be very important when you get to higher level courses in your polymer science courses, because how those steps occur determines your molecular weight distribution of your polymer and the material and the properties of those particular materials. So, we're just scratching the surface this semester. So, this is an example of a free radical halogenation of ethane with chlorine. The first step in the initiation is the chlorine gets split to give 2 chlorine radicals, right? You'll notice that we use 2 single barbed arrows to show that sigma bond is heterolyzing or homolyzing. Homolyzing, right? So it's a homolysis reaction. 1 electron goes with each chlorine atom, and so you end up with 2 chlorine-free radicals. We have just gone from something that had a complete octet to a radical species. That is an initiation step. No radicals on the left, radicals on the right. The chlorine radical then enters into the propagation step, where the chlorine radical abstracts a hydrogen atom from ethane using 3 single barbed arrows. We generate HCl as one of our products, and we generate a carbon-centered radical. How do I know that this is a propagation step other than the fact that it says propagation? I have a radical on both sides. That's what propagation means. One radical beget another, okay? Now, it turns out that this particular reaction has a second propagation step. This radical now reacts with the chlorine that's around to generate the product plus another chlorine radical. What happens to this chlorine radical? It goes back into the propagation step. And this continues until what? Until what? Okay. And then what starts to happen? Termination. Okay? What you all need to know, in all free radical reactions, the concentration of a free radical at any given moment in time, as long as there's plenty of materials around to react with, is essentially 0. What does that mean? I'm obviously drawing a lot of free radicals, but the concentration of those free radicals at any given moment in time is essentially 0. What does that mean? And why? As soon as it's created, they tend to be consumed. And why is that? Because they're extremely reactive. That's right. So as long as the concentration of free radicals remains close to 0, are we going to have termination steps? No, because what are the odds of 2 free radicals coming together and combining with one another? If the concentration of the free radicals is essentially 0, the probability of them coming into contact with one another is essentially 0, right? And so termination does not happen as long as we have plenty of starting materials around. As long as we have plenty of chlorine, as long as we have plenty of ethane around, we're going to initiate the reaction and the propagation will continue. At some point, as Savannah mentioned, we're going to run out of either chlorine or ethane. When that happens, what happens to the radical concentration all of a sudden? It increases, and it increases dramatically. And when the concentration of free radical species in solution, or the gas phase as this is, increases dramatically, then what step starts to take over? Termination, because now the probability of these radicals coming together and combining or reacting with one another is actually quite high, okay? And what you'll notice is that there are many different types of terminations. So for example, 2 chlorine radicals could come together to form molecular chlorine. That's a termination. It's a termination because I'm removing radicals from the system. I could have 2 ethane radicals come together to form a molecule of butane. That would be a termination. I can also have a chlorine radical and a ethane radical combine to form product. Okay? And if you do a very careful analysis of these reaction mixtures, what you will find is that you will have traces of things like butane, right? And you'll have a little leftover chlorine. They'll be in tiny traces, but you can detect them. Okay? And so those are all products of termination. Okay? So you need to be able to identify initiations, propagations, and terminations, and you need to know all those details that we just talked about. Okay? That the free radical concentration remains essentially 0 under propagating conditions. As long as there's plenty of starting materials, those radical concentrations are going to remain quite low. Okay? So let's look at some example problems from the ACS study guide. Which of the indicated sites would most readily undergo hydrogen atom abstraction to generate a radical? Three? 4? I hear 4, I hear 3. It's actually 2. Why is that? Ah, you tell me. It is. So if we look at this molecule, right? If I abstract the hydrogen here, I get a radical, which is what? It's not only tertiary, but it's also allylic. So I can draw resonance structures for it, right? So I can draw a resonance structure for that particular radical. And resonance structures stabilize the system, right? So those are resonance structures of one another. If I abstract here, I get a tertiary radical, which is just, it's more stable than some of the others that you could generate, obviously, but there's no resonance, right? So that's really what that question was asking. It was really about radical stability. Which of these reactions occurs during the free radical chlorination of methane? Or each of these reactions, occurs in the free radical chlorination of methane. Which step corresponds to the first propagation step of the reaction? Propagation step. So what can we eliminate? We can eliminate the first one, A, because it is an initiation step, and we can eliminate because it is a termination step. That leaves us with C and D. It is C. The chlorine radical is the first step in that propagation step. It abstracts a hydrogen atom from the alkane, in this case methane, generating the methyl radical. D is the second propagation step in that reaction. Okay? All right. We're probably not going to get through everything today, but we're going to start talking a little bit more about free radical halogenation. It is one of the few free radical reactions on a laboratory scale that is actually practical for most chemists. We'll talk about the fact that bromine has some selectivity. We'll talk a little bit about oxidation, and then we'll talk a little bit about polymerization. I'm not going to spend a whole lot of time on polymerization because we've got a whole building across the street that devotes its entire existence to that. And so you can learn an awful lot there by taking courses from them. I'm just going to introduce the idea of how polymerization works in a free radical process. So, as we talked about, the initiation step of a free radical reaction involves the generation of radicals, right? So chlorine goes to two chlorine radicals. Usually we initiate this with a bright light, and that's what H nu stands for, right? For those of you who've had your physics, you know that that stands for light. Here it's typically UV light, so strong, intense UV radiation. My laboratory has such a light source. It's called a Hanovia lamp. It has an entire hood dedicated to itself, and it's extremely bright. It's about as bright as the surface of the sun, and if you were to open it up while it was running, you would get a pretty severe burn. So we're not talking about, you know, shining your little flashlight on it, okay? We're talking about some serious light here, okay? Or some serious heat to generate the chlorine radicals, right? And we know that in the propagation step, one radical creates another radical, right? So we generate the methyl radical plus HCl, and that then reacts with the additional chlorine that's around, and you generate your product. Okay. And then, of course, we've already talked about termination steps. I won't spend too much time on this. This is really more review because we were supposed to start with this today. And so there are many different ways in which you can terminate, all of which are legitimate. On the exam, I quite frequently just ask for a termination step instead of all termination steps. Okay? So if that's the case, then everything, you know, just draw one that's reasonable. You can look at the parameters for these types of reactions, and what you'll see is that, you know, you've got to put energy in, obviously, to break a bond. And so we're breaking and forming bonds here, but it's still endothermic, this first step. The second step is actually quite exothermic. And when you sum all this type of stuff up, you get actually a very exothermic reaction. And what you'll find is that free radical halogenation with chlorine is actually very easy to do. The energy of activation for this particular reaction is actually quite small. That has some good points, and it also has some bad points. The good points are it's easy to chlorinate organic molecules. The bad thing is that you get a mixture of products. Just like the other day when we talked about the free radical chlorination of methane, I told you that you got methyl chloride plus dichloromethane plus chloroform plus carbon tetrachloride. That's really only practical on an industrial level because if you're coming to work in my laboratory, we only want you to make what we want, right? We don't want a series of things that we have to separate. And the reason that you get this unselectivity is because the energy of activation for a chlorine radical abstracting a hydrogen atom is actually quite small. That is not true for bromine. Bromine is actually quite selective. Bromine has a very high energy of activation. And so what does that mean then? Bromine radical has a very high energy of activation for abstracting a hydrogen atom. So why would that be beneficial to me in the laboratory? Why might that introduce to me some practicality? It's only going to react if it gets enough energy, that's true. And it's only going to react with the most reactive hydrogen. Whereas chlorine will abstract primary hydrogens, secondary hydrogens, and tertiary hydrogens, right? It will do all of those things at the same time, basically, in the same pot. Bromine does not. Bromine typically only abstracts tertiary hydrogens or allylic hydrogens. Those are the ones that it likes to go after. And so it gives us a way to actually practically use this free radical chemistry to do some useful halogenations. Okay? So we need to know about these relative reactivities. Okay? We know that fluorine is extremely reactive. In fact, it is so reactive that it goes boom, so it's not practical. Fluorinations actually are very important reactions these days because more and more medicines are containing fluorine. So how do you introduce fluorine into an organic molecule without it blowing up your production plant? So there's a lot of energy spent and resources spent in figuring out how to get fluorine into molecules. But it's not really practical on a laboratory scale. Chlorine works pretty good, but it's very reactive. And then bromine and iodine really doesn't react at all. It's pretty stable. So the iodine radical, you can generate it. You can do some things, but it's practically unreactive for our purposes. Okay? So chlorination and bromination is kind of what we are limited to. Okay? And I don't expect you to know all of the numbers here. Okay? That's not the important thing. The important thing is that you see that fluorine's very reactive because of very negative numbers. Iodine, overall, if you look at the numbers, it's positive, right? So not reactive. So you can actually use your Gibbs free energy type calculations that you did in general chemistry to figure all of this out, okay? But what you can see is that chlorination and bromination overall, when you look at these numbers, are the ones that are kind of practical. And bromination is the one that's going to be the most selective, okay? So let's look at the chlorination of propane. Propane, right, contains both what types of hydrogens? It contains primary hydrogens and secondary hydrogens, right? And so if I had Anna come in with a bottle of propane, a bottle of chlorine, and photolize this in the hood, she would actually find that she would get about 45% 1-chloropropane by GC analysis, and she would get about 55% of 2-chloropropane by GC analysis. Okay? And then I would ask her, well, tell me something about the reactivity of those two types of hydrogen. And she can actually, with this data, determine the relative reactivities of those two types of hydrogen for this particular thing. What she's going to need to know is the statistical factor. And she would easily obtain this. She knows that there are 6 primary hydrogens, the 2 methyl groups. And there are 2 secondary hydrogens from the methylene. And simple math, right? That tells you that you've got a 3-to-1 statistical ratio. That statistical ratio tells us that if all things being equal, if it was just based on the chlorine radical randomly running into a hydrogen atom to abstract it, you should have 3 times as much 1-chloropropane as 2-chloropropane. But not all things are equal. The 2 types of hydrogen are not equally reactive. Okay? So she's going to figure out what the intrinsic reactivities of these 2 hydrogens are towards the chlorine radical. And so she's going to calculate that for us. So the calculation is actually quite simple. Okay? We know what the product mixture is. It's the concentration of 2-chloropropane over 1-chloropropane. Okay? Why did I put 2-chloropropane over 1-chloropropane? Why didn't I do it the other way? Is the major product. Always put the major product on top. There's nothing that forbids you to do it the other way as long as you keep everything the same. But kind of as a rule, we like to put the major product on top. Okay? So you get a whole number, well, close to a whole number. So we got 2-chloropropane over 1-chloropropane. That's equal to 55 over 45. She got that from her GC analysis, right? She integrated those 2 peaks. And she knows that that's equal to some type of statistical factor times the reactivity of the secondary hydrogen over the reactivity of the primary hydrogen. Again, it was the secondary product, the secondary hydrogen. You just have to keep these on the same side, okay? And so when she does a little bit of arithmetic, right, she knows that the statistical factor is 1 to 3. She knows the relative reactivity. She can simply, again, do a little manipulation with the equation, and she finds out that that relative reactivity is 3.6 to 1. That tells me that that secondary hydrogen in propane is 3.5 times more reactive than the primary hydrogens. That's why you get more of the secondary product than the primary product, even though there are fewer secondary hydrogens. It's over 3.5 times more reactive. Okay? I rarely tell you that there's going to be a problem on an exam. You will have to do this type of math on the next exam. Okay? You need to be able to look at a problem like this and figure out the relative reactivity of hydrogen atoms in a free radical reaction. It's straightforward algebra. The toughest thing for you to determine is the statistical factor. Okay? Not all hydrogen atoms have to be in that statistical factor. It's only those hydrogen atoms that are reacting. In this case, it was the primaries and the secondaries. Okay? And she saw two products. Now, if we look at the chlorination of isobutane, so again, she does this reaction. She takes isobutane, chlorine gas, shines a bright light on it. She finds out that she ends up with 63% isobutyl chloride and 37% tert-butyl chloride. We can go through and look at the statistical factors again. We can go through and calculate the relative reactivities. It's pretty straightforward, right? What she would find in her calculation is that the reactivity of that tertiary hydrogen is over 5 times more reactive than a primary hydrogen in this free radical chlorination reaction. Okay? And she would go through the math, because the statistical factor here is 9 to 1. There are 9 primary hydrogens and only 1 tertiary hydrogen. She would set the reaction up again. Here they put tert-butyl chloride on the top and isobutyl chloride on the bottom. I would have flipped it, but it's okay. You just have to keep the ratios right. So 37 over 63, we know what the statistical factor is. It's 1 to 9, and then we know this is what we're solving for. And so when we do that, we get the number of 5.3 to 1. Okay? So we know now that a tertiary hydrogen is about 5 times more reactive than a primary hydrogen in a free radical chlorination. Are these numbers going to be identical for bromination? No. Bromine is going to have different relative reactivities. Okay? And so we'd have to go through and calculate those. Okay? So for example, Anna takes isobutane. Now she uses bromine, which is a liquid. She shines a bright light on it, heats it up. And what she finds from GC analysis is greater than 99% tert-butyl bromide and only a trace amount of isobutyl bromide. What's the problem with the math now? Pardon? It's hard to know what a trace really is, right? So, Anna, you're looking at your GC. What would you say a trace is? What assumption would we might make to just do a rough calculation?
Call it 0.
Call it 0. Can I divide by 0? So I put in something really tiny, right? I make an assumption.
0.0001.
Okay, so we make an assumption that it's really tiny, right? And we use some numbers. And so what I'm going to do is I'm going to make a very conservative estimate, which is a little unusual for me. And I'm going to call it 99 to 1. All right? I'm going to call it 99 to 1. And I know that this is going to just be an estimate, that it's actually going to be better than that. But it'll give me an idea, right? So we go through and we do the math, right? We know it's tert-butyl bromide, isobutyl bromide. We know it's 99% this, 1% that. I know what my statistical factor is, the reactivity difference. I do the manipulation, and I find that it's just under 900 to 1. I know that it's really got to be higher than that, right? So this is telling me that bromination is actually practical on a laboratory scale, because if I want to make this, I can do this from this chemistry pretty easily. I mean, I'm essentially going to get all of this product. I'll take my product, I might distill it once to purify it. But if I do the chlorination, right, to make tert-butyl chloride, it's not very, because the chlorine radical is just so much more reactive. It will react with any hydrogen it bumps into, right? The bromine radical is a lot more stable. It doesn't do that very well. Okay. Another thing that you need to pay attention to is the fact that free radical halogenation actually generates chiral centers sometimes. So here we have an example where we're taking pentane and we're going to do free radical chlorination. Pentane is achiral. There are no left-handed pentane and right-handed pentane, right? It's just pentane. But now, Chase is going to take this, he's going to bubble chlorine gas through it, he's going to shine a bright light on it, and he's going to get a mixture of products. He's going to get 1-chloropentane, which is just a primary alkyl chloride. It's not chiral. And he's going to get some 3-chloropentane, and it's not chiral. But he's also going to get some 2-chloropentane. That one is chiral. Okay? So how many products did we really generate? We really generated 4. I've got 1-chloropentane, I've got 3-chloropentane, and then I have R-2-chloropentane, and I have S-2-chloropentane. And what's the ratio of R to S in this reaction for the 2-chloropentane? Pardon? It is 50-50. It is perfectly racemic. Okay? Because we're starting with an achiral starting material, we cannot generate chirality from an achiral starting material without some intervention of something else, right? And so it is a racemic form of the 2-chloropentane that we've generated. So if you look at just that one reaction where we're abstracting one of these secondary hydrogens on carbon number 2, the chlorine radical, of course, is going to remove one of those hydrogens, and it doesn't matter which one because it's going to lead to the same intermediate. And it turns out that these free radical intermediates, not always, but quite frequently, are sp2 hybridized. Okay? And so we have a trigonal planar intermediate. This carbon radical then reacts with what in the next propagation step? To make the chlorinated product. What does it react with? It reacts with Cl2, right? Now, where is that free radical actually? Is it actually on the top, or is it on the bottom, or is it actually in both places? It's one orbital, right? They show it on the top, but really that electron's both on the top and the bottom, right? It's never at the nucleus, but it's actually on both lobes contain the electron, really, right? And so if you have approach of the chlorine, let's say from one side or the other, you end up getting either the R or the S molecule, okay? And is there any difference from the top or the bottom here? If the chlorine comes in from the top, is there any energy difference to that than if it comes in from the bottom? Not at all. Why? Why is the top no different than the bottom?
Because there's no electronegative.
That's not a bad thought. But why is it not any different? We'll get to what you're talking about in just a second, I think. What kind of symmetry is there in that molecule right now? It's mirror symmetry. Through that nucleus of that p orbital, the top is a mirror reflection of the bottom. There's no difference. Chlorine can't tell energetically whether it's approaching from the top or the bottom. Approach from the top may give you the R, approach from the bottom would give you the S, and that's 50-50 because there's no energy difference. Okay? So you end up with a perfect racemic mixture, okay, because of symmetry. Now, that's not true when you have a molecule that already contains a chiral center. So for example, if we took S2-chloropentane, so it's not racemic here, This is our starting material. And we put this in the presence of chlorine and do the free radical chemistry. The chlorine radical from the initiation step will now abstract one of these hydrogens. Okay? And you end up with the same radical. But is approach from the top or the bottom now the same? It is not. Because as you see it right now, the top has this hydrogen on the same side, and the bottom has the chlorine on the same side. There's no mirror symmetry. So approach from the top is different than approach from the bottom. And so you end up with a pair of diastereomers, right, because this center wasn't changed. The second center wasn't changed. I got confused there for a second. But we have now a new chiral center, and anytime we have two chiral centers, we have diastereomers, right? And so we can generate either 2s3s 2,3-dichloropentane or 2s3r 2,3-dichloropentane. And are we going to generate those in equal amounts? No, we are not. Because diastereomeric transition states, that is transition states that lead to diastereomers, are not equal in energy. So one of them will be lower in energy than the other, and we will expect to get one in excess over the other. I do not expect you to determine which one would be in greatest abundance. That's for a higher level chemistry class when you start talking about physical chemistry and really talking about transition states. But if you were to predict, which one would you predict to be the major product, the 2s3r or the 2s3s? You would predict a 2s3r? And why would you do that?
Because the chlorines are in different spaces that crowd each other.
Okay, that's not a bad assumption, right? So we know that chlorine has electron pairs around it. We know that the chlorine, diatomic chlorine has lone pairs around it, and so her argument would be that you don't want those lone pairs getting close to one another, and so having them come on opposite sides should give a little excess, right? Not a bad argument, and would be a perfectly valid argument on anything that I would ask you at this point, okay? Now, we learned in the last chapter that if we take an alkene and we add HBr, we can add HBr across the double bond in a Markovnikov fashion, meaning that the hydrogen went to the carbon with the most hydrogens, and the bromine goes to the least, or the carbon that's the most substituted with the least number of hydrogens, right? And that's 2-bromopropane. And we talked about the fact that it wouldn't do the other type of chemistry, right? It wouldn't give you the 1-bromopropane. However, if you take this alkene and HBr and you have either a bright light or a lot of heat or peroxides around, all of these things favor what kind of chemistry? Free radical chemistry. You can actually add HBr across a carbon-carbon double bond using a free radical mechanism and get 1-bromopropane. So it looks like we're adding HBr across the carbon-carbon double bond in an anti-Markovnikov fashion. And that's exactly what we're doing, okay? This proceeds by a radical mechanism, and it only works for HBr. This does not work for HCl. It has to do with the stability of that bromine radical, okay? So, I've got some time. I want you all to help me figure out that mechanism. So we're going to take propene. We're going to react it with HBr in the presence of, let's just say, a peroxide of some sort, and we're going to get 1-bromopropane. I know that there are 3 steps to each and every one of these mechanisms. What are they? Initiation, propagation, termination. So we're going to start with what? We're going to start with initiation. And I write IN for the initiation step. What is the initiation step here? Generate what? Am I going to generate the bromine radical first? Where's the weakest bond? What has the weakest bond up there? the peroxide. So I just initiated the reaction. Okay? Now your book actually says that generating in the next step is also an initiation. I disagree with them, and I'll tell you why in just a moment. But we go into the next step, which is what? We have propagation. I just always abbreviate it as prop. So I have an alkoxy radical that will react with what? HBr. And I generate a bromine radical plus an alcohol. Not a lot of alcohol because I don't have a lot of peroxide initiator around, but I generate some. Your book will call this an initiation step because you're getting the bromine radical, which is actually the responsible species in the rest of the propagations. I don't like calling it an initiation because it's a radical begetting another radical. It is a propagation step. It just doesn't propagate for very long, and that's why they call it an initiation step. Okay, but that's, to me, is propagation step as well. Now the bromine radical comes into propagation step number 2, and what does it react with? The propene. And how does it react with the propene? I can have the bromine radical attacking the number 1 carbon or the number 2 carbon. Obviously, from the product we get, it attacks what? It attacks carbon number 1. Can you explain why? Carbon 1 is the most substituted? It's the least substituted. But why does it attack that one? What kind of radical did I make? Primary or secondary? Secondary. If it attacked carbon number 2, what kind of radical would have generated? Primary. And what do we know about radical stability? Primary is more stable than, or excuse me, secondary is more stable than primary, right? So it's all about radical stability. Again, it's kind of following Markovnikov's rule in a way, isn't it? Markovnikov's rule was all about carbocation stability. This is about radical stability, okay? So now what happens? We move into propagation step number 3. What does this react with? It reacts with HBr and does what? It regenerates a bromine radical. It abstracts a hydrogen atom, generates a bromine radical, plus I just generated my product that I wanted, right? This bromine radical then does what? Comes back to propagation step number 2, and this continues. This propagates. This continues on until what happens? Until we start to get to termination. And when do we start to get to termination steps? Yeah, so maybe we start to run out of bromine or alkene, and all of a sudden the radical concentrations go up, and we start to see termination steps. So what might be some termination steps? Give me just one. Okay, so I can have a bromine radical and a bromine radical reacting with one another to form bromine. What else could be a possible termination step? Two of the what? Okay, so I could have maybe 2 of these coming together to generate, let's see, what would that be? That would be that. So basically any 2 radicals coming together to do that. I could also have one of these radicals coming in to react with another bromine radical to form a dibromide. But this happens at the very end of the reaction when all of the starting materials are pretty much so being converted into product. And so these byproducts or unwanted things actually are in very low concentration or easily to purify out of the reaction. Okay? Does this make sense? Start with your initiation. Go through your propagations. Know that you can have more than one propagation step. How many propagation steps can you have? Well, if you think about free radical polymerization, you can have thousands of propagation steps. I'm not going to ask you to do 1,000 propagation step type of thing. And neither will your professors over in polymer science. You just say it's in propagation, right? But what I'm showing here are 3 unique propagation steps. I'm not showing that the bromine radical now comes back into step 2. I just know that that's what happens, right? Until I start to run out of materials and I go through termination, okay? So I'm going to come back to this why is free radical chemistry important slide that I showed you, right? And I know many of you want to go into the health professions. And we've already talked a little bit about oxidation being responsible for aging. I breathe in oxygen, my organic molecules in my body get oxidized. That's how I get energy. It's also how I age. It's also the cause of disease, okay? So how we control these free radical processes is very important. And so one of the things that we talked about, right, was that arachidonic acid, which is a common lipid that we have in our diet, right, can get oxidized to these things called prostaglandins. It can also get oxidized to other things. Have you ever seen cooking oil that sat out too long and it started to turn turbid? What did your mom call that? They said they might say it went bad or it became rancid, right? What does that mean? Rancid just means that it's spoiled. It became oxidized, okay? This is what happens to our body. We actually go rancid when we breathe in air, okay? But we have to have mechanisms that help fight that, okay? And one way in which we do this is through our diet, taking in antioxidants. We've already talked a little bit about it, okay? This molecule is vitamin E. It is one of your most powerful antioxidants in your system. Would you say that that is fat soluble or water soluble? It is fat soluble. It exists in fat globules that are floating around in your blood called HDL and LDL. Does anybody know what those are? Cholesterol. Well, you all know them as cholesterol, but it's actually more than just cholesterol, right? But you've got good cholesterol and you've got bad cholesterol. Both of them contain vitamin E, okay? They contain vitamin E because those fat particles like to get oxidized, like arachidonic acid, okay? Cholesterol. And when they get oxidized, they actually form plaques. And those plaques deposit, because they're not water soluble, they deposit on your arterial walls, and this is how you get atherosclerosis, heart attacks, strokes, all that kind of stuff. It's all free radical chemistry, okay? So vitamin E is actually a very potent antioxidant. Is vitamin E chiral or achiral? It is chiral, right? There's a chiral center right there, there's a chiral center right there, and there's a chiral center right there. It is a chiral molecule, okay? Vitamin E is again, used in anti-aging creams and all kinds of things. It's a part of your diet. For those of you who might like prepared sausages, kind of like I do, one of the things is sausages are full of what? Fat, right? They're full of fats. And fats are lipids, and lipids oxidize. Sausage actually goes rancid really quick if you don't put some type of antioxidant in it. Well, it turns out that vitamin E is kind of expensive, and sausage you usually sell kind of cheap, and so they put in what's called BHT, okay, which is kind of a synthetic version of vitamin E. It stands for butylated hydroxytoluene, okay? Easy to make, but it's synthetic, and it does about the same thing, more or less, that vitamin E does, and it's used to package these types of things like Vienna sausages and bratwursts and stuff that you don't want to just spoil real quick, okay? The way that these work is that OH bond on a phenol can actually donate its hydrogen atom to a carbon-centered radical. And so you have these reactive radicals that are not good for your health that get reduced by picking up a hydrogen atom from the hydroxy group of the phenol. And it turns out that this phenolate radical, or phenoxy radical as some people call it, is actually stabilized by resonance. And if it's stabilized by resonance, is it going to be more reactive or less reactive? less reactive. The more stability, the less reactive, right? So is it going to cause damage or less damage? It's going to cause a lot less damage, right? So we get rid of the damage-causing radical and we generate another radical which is more stable. That's what vitamin E does. This is also why it's important that you also have vitamin C, because vitamin E is in a fat globule, and it turns out that this radical gets reduced by the vitamin C that's water-soluble in your blood. So the vitamin C to vitamin E ratio is actually kind of important to your health, okay? Because the vitamin C turns around and reduces that vitamin E so that it's back to an antioxidant within that fat globule, okay? And then you can excrete the byproducts of the vitamin C because they're water-soluble. Okay, so it's very complicated when you really think about it. Kind of hurts your head. Okay. Polymers and polymerization. So just a couple of things that I want to mention here. You have these things called monomers, and we can actually link them together to make polymers. And quite frequently, although not exclusively, this is done by free radical chemistry. So for those of you who've ever picked up your milk jug in the morning and looked under it and you saw HDPE, that stood for high-density polyethylene. And polyethylene is taking ethylene and polymerizing it into a big, long alkane that weighs an awful lot. And it has these plastic properties that make for nice, really nice milk jugs, okay, among other things. And so these all occur by free radical reactions. Some other polymers that are made by free radical reactions are polyvinyl chloride, PVC, polypropylene. This is what AstroTurf is made out of. Okay, it's made by a free radical reaction. And your Starbucks cup, that is styrofoam, right? Made by taking styrene and polymerizing it into what's called polystyrene. Makes a really good insulating material, okay? All of these are done by free radical reactions. Now, the way that these reactions work is that we still have the same three steps: initiation, propagation, and termination. And so let's just say we take styrene and we're wanting to make a styrene cup, right? Or the material to make a styrene cup. You would take an initiator like a peroxide, you would add it to the styrene. The peroxide decomposes into the alkoxy radicals. Those alkoxy radicals then, in a propagation step, see, this is where me and the book differ, actually adds to the carbon-carbon double bond, and you get a carbon radical. That carbon radical then reacts with more carbon-carbon double bond, and this is how you make those carbon-carbon bonds. And this can happen thousands of times before termination happens. And so you can end up with a very large molecule that has a molecular weight in the thousands, if not hundreds of thousands of molecular weight units. And then, of course, you can have terminations where the two carbon-centered radicals can come together, or two of these radicals, or whatever, come together and terminate the reaction. Okay? So, that's it for today. I think on Friday I think the next thing in the list was for us to have a problem-solving day, I think, or something like that. So we'll be doing that on Friday. Be prepared to work at the board. I'll come in with some problems, and we'll break up into small groups, and we'll do some mechanism kind of problems at the board. So have a great day, and I'll see you on Friday.